Good afternoon, everyone, and welcome to this joint EOL seminar with CISL, the Computational and Information Systems Lab. We have invited a unique speaker, both in topic and in research background, to EOL. I am pleased to introduce Dr. John Schreck, who joined NCAR recently as a machine learning scientist at CISL with the Analytics and Integrative Machine Learning Group, where he is helping develop machine learning applications for the various earth science research done at NCAR. Dr. Schreck received his PhD in physics at Drexel University in Philadelphia and went on to do a postdoc at Oxford University in England and finally at Columbia University in New York at the Department of Chemical Engineering, where he started applying machine learning techniques. He did a short stint with a private company merging machine learning and e-commerce before arriving at NCAR, where we are benefiting from his expertise. I had mentioned that John is part of a team at CISL developing machine learning applications for NCAR research. Specifically, he is collaborating with EOL researchers to improve holographic image processing for the Holodeck 2 cloud probe, operated by RAF, our research aviation facility. And this is all using machine learning. John's seminar title is entitled Neural Network Processing of Holographic Images. We are using Slido to pose questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your question pop up immediately, because we're archiving all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. John Schreck, we welcome you, and the virtual stage is now yours.
Thank you very much, Jackie, for the very nice intro. As you can see, the title of my talk is Neural Network Processing of Holographic Images, and I want to point out my co-authors are Gabrielle Gantos, Matt Heyman, Aaron Bansemer, and David John Gagne. Myself, Gabrielle, and David John are all from CISL and the AI/ML group. Matt Heyman is from EOL, and Aaron is from M-Cubed. Play over here. Okay, so I just have a relatively brief overview slide here, just to kind of give you an idea of where I'm going to go with this talk. So the first couple of slides are going to mostly just sort of deal with what kind of holograms are we interested in processing, where do they come from, what's in them. And the other key that I'll introduce briefly is how are we going to do it? And there's sort of two components to our approach to processing holograms. As you can see listed here, the first key is neural networks, leveraging those as part of our framework, and also GPU and parallel computing. So these are the main ingredients that are going to go into the whole, basically everything I'm going to show you today. So after I do a little bit of intro, I'll kind of digress and get into a little bit of the weeds and discuss our operational pipeline and how we train and optimize the neural network models, because that's effectively what this talk is about. It's a new approach to processing holograms. Of course, you're going to want to see some results from this new approach. So I will show you a comparison of how the model or our approach is performing on real versus sort of less real or synthetic holograms. And then I'm going to show you how the importance of noise and when it comes to training these neural network models. So then I'll compare our results against the only other processing package available that's processed the same holograms. And hopefully, if I have enough time, I'll give you a little bit of a sneak peek on kind of where we're going next with the research involving holograms. And I will say that it involves generative models, or these deep fakes, as you may have heard them referred to as before. So, okay, to get back to the main topic here is really the Holodeck instrument, as was pointed out by Jackie, which is operated by RAL. So Holodeck is a second generation instrument, which is designed for cloud particle characterization and sizing. The instrument captures inline holograms of cloud particles by transmitting a laser pulse between the probe arms and imaging the interference of the incident laser field, and that's scattered by the cloud particles onto a CCD. So in this picture here, you can see Holodeck. It's actually outfitted on two airplanes here. It's this little guy right here. I'm kind of circling it with my cursor here. You can see the arms here, the probe, and here is Holodeck 2 outfitted onto a C-130 up here in the larger image. So Holodeck was designed such that it has quite sufficient resolution to determine very small objects in these holograms, mainly like cloud droplets, liquid droplets, as well as ice crystals. And I'm going to show you some examples where it picks up other things that I'm just going to refer to as artifacts. So the data that we're interested in here is basically comes from what is called the Cloud Systems Evolution and Trades Project, or CSET for short. And CSET was a number of runs with the holodeck detector that were flown on an airplane, and I have the date here, between June 1st and August 15th back in 2015. Okay, and there were many different flights obtaining lots of different holograms. And in particular, we're going to focus on one of the subsets of the CSET, which is called the RF07 subset. And in this picture here, I'm showing you the flight path of it. Okay, so I think if I got this right, the probe took off from Hawaii sometime in the summer of 2015, flew around the Pacific Ocean, and then wound up landing up there in Central California. I think it was Sacramento, as you can see here. So, this is sort of summertime, right? It's pretty warm in this region. And as far as I know, most of the clouds that were captured, that the plane flew through to obtain these hologram images, were mainly cumulus clouds. Okay. So here's an example of one of the holograms obtained from RF07. Okay, and because these were sort of obtained in the summer and a part of the Earth where it's relatively warm, it's mostly going to be free of ice, the examples that we have considered for this project. And we're mainly interested in trying to back out the liquid particles of these, okay? So this picture here kind of shows you an example, and they're huge, right? I mean, this is a megapixel size image, okay? So if you look at the X and the Y dimensions, it's thousands of pixels in each direction. Okay, and you can see that when that's converted into like physical units, it's about 14 millimeters by about 9.5 millimeters in the plane here of what's being imaged. Okay, so but that actually winds up being quite a small pixel resolution. It's 2.96 micrometers per pixel in both X and Y in this image. Okay, now I want you to kind of note the little zoomed in box that I have here with the orange block. That is a 512 by 512 pixel subsample of this image that I've kind of just blown up for your convenience. Because if you just sort of look at this hologram all by itself, you can't really see that much, right? You kind of have to squint, and furthermore, it's already in a two-dimensional plane for you, the viewer. So if you kind of look carefully at the zoomed in image here, you can kind of see some interference patterns, some, these circles that seem to have, there's a center, and then there are these circles that are kind of emanating away from the center. So that is what we're going to find out later is a particle in there somewhere, okay? And in this particular example here, most of the holograms that we're going to look at only contained up to a couple hundred particles, but there's lots of other examples in the CSET that have a very broad range of particles, some that even contain up to 10,000 particles per hologram, okay? So the current way that we can analyze these holograms, or that I'm referring to here is the identification program. I'm going to just refer to it as the standard method. Okay, so through the rest of the talk, when I refer to the standard method, it's the only other package that I know that exists that we can use to process the holograms. So the way that the standard method works, and I'm not going to get into too many details. I left you references 4 and 5 here, which I'll show you later, where you can get all the details, and you can also refer to our paper. But the standard method ensures it does not utilize machine learning. What it does do is it utilizes a range of pre-selected filters, and each one of these filters is applied to the hologram when the hologram has been reconstructed at different planes along the axis of the detector, which I will give you a few more details on that in a couple of slides. So from these applied filters on these holograms, the maximum and the peak intensity versus filter particle size can be used to estimate the true particle size, okay? So the RF07, the data set that we're going to look at in particular here, utilize what we're going to just say are custom rules, which is really sort of a hand-tuned approach to kind of being able to process large numbers of these holograms, okay? This is the custom rules that we're using here that we didn't really use, that just sort of were used to process this data that I'm using. You can read about more of that in reference 5 here, okay? But at the end of the day, pretty much all of the rules that went into using the standard method to process the holograms are about the same across the data sets, okay? So what the main objective of this talk is, can we use machine learning to process these holograms, okay? Only the standard method exists as far as I know, and there are no machine learning approaches that can do the full scope of what we want. Okay, so one of the main potential advantages of using a data-driven method is that potentially, because it's a neural net involved, we might be able to use a neural net to learn about lots of different types of holograms. Okay, and now today I'm mainly going to show you results that have liquid particles, but we are optimistic that future studies, that a neural net will allow more flexibility in terms of learning different things in the holograms without having to use custom and fine-tuned rules. Okay, so another main reason why we would like an alternative or even just another method to process these holograms is because it's hard to check the accuracy of what we have currently, the standard method, because that's the only thing that's available. Okay, so even just having another benchmark available can tell us more about the performance of both these methods. Furthermore, the standard method can be slow depending on the type of hologram that you're processing with it, as well as what's in it. And it may take quite a long time to process a full field campaign, which can be tens of thousands of holograms. Okay, and that could be weeks. So ideally, it would be great that if we could use machine learning to perform real-time processing, which would be several holograms per second. That's quite an optimistic leap from weeks to seconds. So for today, I'm going to aim for days to process 10,000 holograms. But that is the ultimate goal with future extensions of our work here. Okay, so because we don't have truth labels with holodeck holograms, we're not forced, but we've decided to resort to creating a synthetic set of holograms. Okay, and what I mean by that is synthetic holograms are produced using the same physical model of the instrument and the same optical settings of the instrument. Okay, so note this is an example of a synthetic hologram. It's a lot cleaner than the one I just showed you, right? There's no noise in it. This is effectively a perfect hologram, okay, because we did not yet introduce any noise. Every single one of these holograms that we generated has 500 particles in it. The particles are themselves distributed randomly along X, Y, Z, and we sample the diameters of these particles from a gamma distribution. Okay, and because we wanted these synthetic holograms to be very similar in size and other details relative to the holodeck holograms, we generated these basically assuming that they were positioned between 14 and about 160 millimeters from the detector arms. Okay, that's pretty close to the same operational range that the standard method was used to process on the data sets that I'll show coming up. So we generated 3 splits or sets of these holograms. We generated 100 of them to be used in order to train a neural net. Then we generated a second set of 20, a validation set, and then a true holdout set, which we're going to just call the testing set, was 20 holograms. Okay, so remember, each one has 500, and they're all megapixel sized, and everything is identical in terms of optical settings between the holodeck and the synthetic holograms. So before I go farther and get farther into the weeds of our pipeline, we needed to manually label some of these RF07 holodeck examples. Okay, and the main reason is because we need a way to benchmark how well the model is going to perform, as well as this enables us to compare against the standard method. Okay, so basically 4 of us here at NCAR manually labeled about more than 2,000 examples of these, as you can see here. So the top row kind of is showing you examples of particles that we labeled to be there or existing. I'm going to use the word in focus going forward, okay, because the particle is basically a small little dot there that is proportional to the shape of the particle. The bottom row shows you examples of images that we labeled false or does not contain an in-focus particle. Okay, and as you can see that a lot of these examples are like kind of subjective. I mean, for instance, the one that's labeled false here, this is actually a reflection, okay, which I did not know what that was. I had to have my colleagues Matt and Aaron explain to me that this is not a real particle and that it should be labeled false, and we don't want the neural net sort of predicting a particle on examples like this. Similarly, this one over here, all the way over here on the bottom right, if you kind of focus at it, it sort of looks like a dark and a light spot, kind of sort of symmetric and kind of blob, like stuck right next to each other. And you probably can't really see in this image, but if you focus real hard, you can see lots and lots of these funky little particles that we labeled false. So these are some kind of artifact. I'm not quite sure exactly what it is, but it is not this nice round, kind of smooth dark circle like we're seeing up here in these darker images. Okay, so because some of these were really subjective, we kind of decided to try to give it a confidence score. So basically, like a lot of the examples on the top had a confidence score of 4 or 5, meaning like, yeah, we're pretty sure it's there. But a lot of the examples were subjective, as we said. So we wanted to give ourselves some flexibility in some sense by means of a confidence score. So if we were just not confident at all, we just said, all right, I'm not confident, it's a 0. Okay. So we did 2 rounds of this. We're going to call them the train and the validation splits, and I'll explain how I use these later. Round 1 contained about 1,202 examples, and of the 1,202, 367 were labeled to contain an in-focus particle. Round 2 contained 1,154 examples, and there we had 890 of them were labeled to be in focus. So they're not quite perfectly balanced, but they're not too imbalanced either. Okay, so I'm just going to keep going. So this is main key number 1, and I'm going to show you main key number 2 to our pipeline. Okay, and this is, I've already used the word wave propagation and refocusing the hologram, but I haven't told you what I mean by that. Okay, so the tiger flying the airplane is supposed to be us operating a holodeck. And you can see that it shows the incident wave here being kind of shot forward in front of the airplane. At the one plane here where you see P0, there's a particle. Okay, and the laser beams are going to strike that particle and they're going to get scattered. Okay, and you can see over here where I have the plane labeled P1, right? That's where the scattered wave is going to wind up. So if you were to observe from that plane, the capital X, Y, Z, you wouldn't see a nice little dark circle like I just showed you in the last slide. You might see these rings like I showed you earlier. Okay, so in other words, what we can do, because a hologram is not like a conventional image, a hologram gives us the phase information, okay, because we're working with electric fields here of the scattered wave and the reference wave. Okay, and as a result of that, because we have the phase, we can basically refocus this hologram at some Z away from where we're currently viewing the hologram. Okay, and so the way that this is a mathematical calculation that involves Fourier transform and then taking an inverse Fourier transform. But at the end of the day, what that allows us to do is take a plane at one value of Z away from the detector arms and basically like remake the plane, but at some other distance Z away from the detector arms. And the whole goal here is we want to take scattered particles and focus them, okay? One other very important thing to note about this propagation is that we perform this calculation on the GPU now. And I won't get too much into the time comparison here, but you can see my paper on that. We are able to bring down this calculation by at least a factor of 10 by performing this with PyTorch 1.9, which started supporting the Fourier transforms natively, okay? So that's key number 1, but this also lets me kind of explain to you how we're going to use a neural net, okay? So the top and the bottom rows here show a holodeck example on the top and then a synthetic example on the bottom, okay? And both the little insets are what I showed you earlier, right? So the image in the column on the left here, these are out of focus, okay? So what the image here in the center column here is now showing us having performed the wave propagation calculation on the hologram, and we refocused it just at some other value of Z away from the detector. Okay, in both cases, different values of Z. The particle then has gone from, right, these emanating circles. And in the case of the top particle here, it's actually a relatively small particle once it's in focus. Okay, and then the bottom example just shows you another view of that from the point of view of the synthetic holograms, right, the ones without noise. Okay, now at the end of the day, I'm going to draw this thing over here I'm going to call a mask, okay, and it's supposed to be a little dot here basically drawn over top of the particle when it's exactly in focus, okay? If I'm able to have a neural network predict this image over here, which is to say have a neural network draw in a little dark circle when a particle is in focus, I can then estimate the diameter from that, okay? And because I wave propagated it to some value Z, I at least know the Z value that I wave propagated to. So in other words, that means I have X, Y, Z, okay, by performing, by thinking about the problem like this, trying to essentially say, okay, I want to input this image here into the neural net, and I want to predict this on the way out, okay? And that's exactly my key number 2 here, okay? So this is the second step in our, and this overall our pipeline here, okay? And that's the goal. I basically just said what it is, right? You want to, the image on the top shows a small subsampled image, a tile, going into the neural net, and the neural net's supposed to predict nothing. It should predict an image the same size as the input image, but is all zeros, okay? Because there's no particles in focus, okay? So the bottom example shows you when there is a particle in focus in the input image. Okay, so this model goes into this neural network here, and don't worry about the details. It's just a drawing meant to represent a neural net. And the task now is to predict the mask around the in-focus particle at the XY, the center of the XY particle. Okay, so this is what we want a machine learning to do, right? And I noted in the previous slide that if a model is able to do that, then we should be able to back out the X, Y, Z, and D coordinates for all of the particles in these images. Now, I want to quickly note too that the example that I'm showing here, I'm just showing one particle, but there can be more than one particle in focus in one of these small little tiled images. The type of machine learning model, the neural net that we've employed here, is capable of doing that. So in other words, we can predict an arbitrary number of particles per image. And again, I want to note that we can only really use synthetic data to train on, because that is the only data that we have the true labels. Okay, and what I mean by that is we position the particles where we wanted to when we generated these synthetic holograms. So we know exactly where X, Y, Z, and D is. We do not know that for the holodeck examples. Okay. All right, so I kind of just added the slide last minute here, but I want to make a point about how we use these neural nets, okay? And there's a difference between how we're going to train the neural net and then how we're actually going to use the neural net when it's in operation, okay? So in other words, we have a trained model and now we want to use it, okay? So, but just to quickly mention how we train this model, I noted earlier that I had 100 synthetic holograms, okay? And each one of those holograms contained 500 particles. Okay, so what we went in, we said, okay, let's go in and grab out, let's get in a picture or a subsample, 512 by 512 pixel tile of the original hologram that contains all of the in-focus particles. Okay, so in other words, we're going to say, if we have 100 holograms, we have 500 particles in each, we're going to have 50,000 512 by 512 examples that have an in-focus particle. Okay, then what we're going to do is we want to sample one-to-one. Right? Like images having particles in focus, images not having particles in focus. So the other 50%, e.g. 50,000 images, is going to be split 25% between images that just don't have a particle in focus. Okay, and then we're going to have images that don't have a particle in focus, but it's one Z plane away if you're thinking about propagation. Okay, where that Z could be 100 micrometers, it could be 1,000. Kind of doesn't matter, but the point is that sometimes when you get pretty close to these particles, they're not quite in focus, but they're getting pretty small, okay? And we want to try to get the model to not be tempted to predict a particle by examples like this. And I'm kind of drawing a little bit of an exaggeration here because there's many cases where a particle is not technically in focus. It's close, but it's slightly, one Z plane away. And it looks very, very, very close to being an in-focus particle, except for the fact that there might be a little dot in the middle. Okay, so we really got to get the neural net to be able to differentiate those examples from the examples where there really are in-focus particles. Okay, now we have the luxury over here to kind of sample these images from these giant holograms all we want. But at the end of the day, when we want to use our algorithm on holodeck holograms where we don't have the labels, we basically have to search the entire hologram. Okay, so when we have a trained model, the pipeline for actually processing the holograms is a little bit different. Okay, so I'm not going to go through every single little detail here. This is all in my paper, but I mainly kind of want to walk you through that. You start with the initial hologram. You'll propagate that out to n different values of Z away from the detector probe. Okay, that choice of n is yours. Okay, now the way that we select that n is we basically say, okay, well, I'm going to search for particles between 160 millimeters and 14 millimeters, and I want to do that in even spacing. So I'm just going to divide by n, where n is the number of wave propagation reconstructions we're going to perform here. Okay, now I noted earlier that we have a resolution of about just under 3 micrometers in both x and y. So if I needed to do that many propagations along the z-axis, that would be 48,648 planes, which is a lot. Okay, so we're not actually going to do that many, but we're going to try. All right, so after you do this wave prop, you then have basically turned the original hologram into n images of the same size, but at different values of z. Each one of these planes is going to get broken up into smaller titles, into 512 by 512 pixels, mind you. They're all going to go through a trained neural net. The neural net's going to have a prediction for each one of the tiles, right? That's what this is meant to illustrate over here. Then all of these predictions have to be reassembled. Okay, so in other words, we've broken them into smaller images. Now we want to unbreak them. We want to put them back together. So up here at this point, we now have n predictions. okay, and reconstructed planes and predictions corresponding to the n planes that we had that we started with. Finally, we need to turn this sort of n planes, which is sort of n two-dimensional predictions, into one 3D prediction from which we can back out the XYZ coordinates of all the particles in there. And we're just going to call this matching. Okay, so I'll go into some more of these details in the slides that are coming up here. But this is the main pipeline. Okay, and note that this is a little bit different from how we train it, right? The whole hologram needs to be searched because we don't know where the particles are. Okay, so because these holograms are so big, and I keep alluding to this, I'm saying we're tiling them 512 by 512 pixels. What we're really doing here is, because it's too big, we can't train neural nets with these giant images. We don't have enough GPU memory, and it would be tremendously slow even if we did with current technology. So we've resorted to basically putting a grid on top of this hologram. Now, the thing that's a little bit different about this grid and sort of a conventional grid is that we have the grid tiles actually have a certain amount of overlap here. Okay, so you'll see that I have a thing called a tile size of 512 pixels. So note that I'm kind of boxing around this red tile. Okay, and then there's another tile, a neighbor tile, this orange one, right? And that is a step size of 128. This is not quite drawn to scale. It's basically every 128 pixels, you get a new tile. Okay, so in other words, we're getting like overlap, okay, between the tiles. And the reason why we wanted to do that was because we were worried about edge cases, right? Like where in this case, for example, there's a big particle here and it's actually spread out across a bunch of different tiles. The last thing you'd want is only one of these tiles actually predicting part of the particle and the other three not doing that, okay? So we basically found there was a need to have a certain amount of overlap in order to kind of deal with this around the edge case, okay? And as I noted in the pipeline figure, every single one of these tiles needs to go through the neural net. The neural net's going to make a mask prediction, right? So this is now the binary image over here. It's ones where you see the black color and zeros where you don't, okay? And then at the end of the day, all of those tiles, of which there's 885 of them, they all have to be reconstructed, which is really just taking a pretty simple average over them. But at the end of the day, you can see that we wind up with a predicted binary image at some z that we wave prop to, the same size as the input image. Okay, so in other words, this thing over here on the right is now also a megapixel size, but it's just zeros and ones, right? Ones where there's supposed to be masks predicted over the particles, zero everywhere else, okay? I won't get into too many details here, but you can read the paper. And we actually, because of this tile overlap, we were not able to simply break down the image while it was on the GPU. And we actually created ourselves a fairly significant bottleneck right here that we're working on figuring out now. I will say, check into the paper. It's not too bad. I will give you a speed comparison right here, but the previous slide basically was just kind of showing the example of one reconstructed plane, right? It's like you got one plane, you break it into tiles, feed them through the neural net, you reconstruct all the tiles back into one full-size image. We got to do that n times, right? Because we need to roll out the wave prop calculation over z, okay? So this is just showing you sort of high level, you know, the full image needs to be tiled, go through the neural net, we get a predicted mask array over here at Z1, Z2, all the way down to Zn, okay? And the reason why, one of the reasons why we chose to design the algorithm this way is because we're going to take advantage of parallelization right here in this step. And this is sort of the key step right here. Pardon me, I just need to get a sip of water. All of the wave propagation calculations that we need to do, remember, you got to do it n times for every hologram, and then you have to break down that plane into 885 tiles. Every one of those can be done simultaneously, as long as it's, you know, they're at a different n, okay? So that basically means that I can process all of these reconstruction planes in parallel. So ideally, the time that it takes to process a hologram is the time that it takes me to process one plane out of n planes, okay? And I benchmarked that here on our Casper cluster here, and I can get it down to about 7.5 seconds per plane. And that includes that crazy bottleneck that I mentioned to you earlier. Okay, now Casper only has 64 V100 GPUs, which are not state of the art anymore. So if we're talking Casper, I can do about 2 minutes per hologram with 1,000 reconstruction planes. Okay, now if I use, you know, AWS or something else, and I just got all the GPUs that I needed, let's just say there's n of them, and let's say that n is 1,000, I can do a field campaign, which is about 40,000 holograms in about 3.5 days. Okay, now that's with V100s. I went over to NVIDIA's website and I was checking out the A100s because I think those are the latest and greatest ones for a very short time period here. Their website says that the A100s are about 2 times faster than the V100, so less than 2 days. If I had those available to me now, which I could do that in 1 hour by spooling up an AWS cluster, N of them if I needed to. Okay, so we've gone from possibly weeks from the standard method down to less than 2 days with our approach here. Okay, so I'm going to keep going in a little bit further into the weeds here, and then I'll get back to the results. So I noted at this point in our pipeline, we're basically just at the point where we have N predicted full size arrays. Okay, but we need to put all these results back together to get a 3-dimensional prediction. Okay, and in the pipeline figure, I mentioned that this was called the matching stage. Okay, so matching is really a 2-step process. And step 1 is this slide, and step 2 is the next slide coming up. Okay, so step 1 involves the individual full-size mask predictions at some N. So just one at a time here. Okay, so remember, like we're supposed to predict 1s where there's a particle in focus, and 0s everywhere else. Okay, but what we need to do is we need to group together particles that are all 1s. So if you kind of imagine this magnifying glass here is kind of zoomed in on this big one up here, we're going to say that these red 1s that I've highlighted, because they're neighbors to each other, either in the X direction or the Y direction, we're going to take them to be part of a group. Okay, and then anytime you have a break between one, so for instance, here I have a red 1, then I have a 0, and then I have a 1. This one over here is going to be part of a different cluster because it's been broken off from this cluster over here by a bunch of 0s. Okay, so if you take my point that what we really want to do is just put 1s together where they're nearest neighbors or not. Okay, and then we want to basically just label them, right? So here we have this unique island of 1s over here. I'm going to label it 0. Oh, we had another one over here. Let's just label it 1. Got another one over here. Label it 2. Okay, great. There's 3 particles in this image. Okay, but the result of that is I now have an estimate of X0, Y0, and D0 for the 0th particle, given that the original image was reconstructed at some value Z away from the probe arms. Okay, so in this example here, all 3 predicted particles have the same ZJ, but they have different X, Ys, and Ds. Okay, so step 2 involves putting the N mask predictions together to get a 3D result. Okay, so that's what the top diagram in here is supposed to show you, right? We have N reconstructions of the original hologram. All of those went through the neural net. And then after we put everything back together, this is what we were with. Okay, so step 2 basically now involves another type of clustering, but we're going to leverage a distance-based clustering here. So you might be familiar with k-means. I use something kind of similar called leader clustering. But the point is, at the end of the day, is that if you consider this particle 0 all the way down over here at Z0, I'm going to compute the root mean squared error between this particle and all of the other predicted particles across all of the planes. Okay, and you do that for every single particle. So you're computing the distance matrix. That's what you use in order to do the clustering when you are given a clustering threshold. Okay, and what I mean by that is if 2 particles, given that I've computed the distance between them, if that distance falls below some given threshold value, they will be considered to be part of a common cluster, not necessarily put into a cluster, but considered. Okay, at the end of the day, when you work yourself through this algorithm, you wind up with particles, some of the particles across these N planes being clustered into a cluster, and some of them are just left unclustered. Okay, but at the end of the day, we basically have M particles, okay, where anytime I have a cluster of particles, I'll take an average across them to get the centroid, and then we'll consider that to be the representative of the cluster. Okay, so at the end of the day, you have P total particles predicted across N planes, but you only have M at the end of the day post the 2-step clustering process. Okay, so it's a little bit, there's a lot going on here, but it's a 2-step process. The first does it in 2D, and then the stage 2 does it in 3D. Okay, so I have 2 slides here. I'm just going to double back on how I train the model, and then we're going to get into the results. Okay, now I noted earlier that we train models only on synthetic images, which means when I went in and I said, okay, I need this neural net to predict masks, well, I had to calculate some kind of metric, right, or a loss function in order to say how well I'm doing, and then update the weights accordingly of the neural net. Okay, so because that's our task, right, predict 1s and 0s, but in 2D, we're going to use something called a dice score, which is given by this, But you can see it's a product over a sum. So it's kind of like an intersection over union. Okay. And what this is going to do is it's just going to encourage the model to predict dark circles where it's supposed to predict dark circles and not predict anything else otherwise. Okay. So this is computed, and that value is then used to update the model weights through backpropagation. Okay. Now I'm showing you this over here. I've already more or less explained this pipeline over here, but this is sort of how it differs from the operational pipeline. And that, if you recall, we just sort of randomly selected some tiles from our holograms, trained the model that way by upsampling one-to-one particles in focus, not in focus, and then basically computing some performance metrics to see how well we were doing. Okay. Now I will say that I found by trial and error that if I threw in a little bit of noise right here at the step, so I've already tiled the holograms in the 512 by 512, and I'm going to throw noise on these images right before it goes into the neural net. Okay, and then the neural net makes a prediction and I calculate the loss. So I found that if we do that, we massively increase our performance on holodeck images. Okay, so I'm implying that if we don't throw in noise, we don't do well on holodeck images. We only do well on the synthetic images, and that is true. Okay, I'm just getting ahead of myself. But I need to state that the reason why I have two splits of the manual label examples, if you recall way back at the beginning of this talk, is because I need a way to toggle the noise parameters. Like I can throw noise in over here, but it's a bit arbitrary if I just throw it in sort of arbitrarily. Okay, so you can kind of imagine I just sort of had some knobs to tune the relative intensity of the noise, let's just say, and there's a couple of different types of noise that I added in here. You can kind of imagine that I just set different parameters to the noise, trained the model exactly as I described it up here, only on synthetic data. But then when the model was finished training, I then went and I predicted on that first split of manually labeled images. Okay. And so, if I ran 100 models and I had just 100 different types of noise settings, you're basically just saying, well, which one gave me the best result on the holodeck manually labeled tiles? Okay. So I just want to be clear. The stuff that's labeled in red was not used in backpropagation. It was only used during hyperparameter optimization to pick out the model with the most reasonable noise settings over here. But otherwise, the model was only backpropped on synthetic data to get that mask prediction up. Okay, so noise was very, very important, as we found randomly. Okay, now I have a little bit of a wall text here. I just want you to focus on the blue row and the red row. Okay, and this is still training results, right? So this is just how well did the model do when I was training it on those random test sets that I made, right? Remember when I was sampling the tiles from the holograms? Okay, and this is 50-50 balance. Okay, so I want you to note that I kind of just skipped right past that in that last slide, but I have these labels where S basically just means if it just has subscript S, it was not trained with noise. If it was trained with noise, I give it the SH, right? Because then I needed those holodeck examples to pick out the right noise parameter. Okay, so these 5 models here were all trained with noise, but just using a different value of N. So in other words, the number of wave prop reconstructions I needed to do. This is a bit of wall of text, and I don't want you to stare at it for too long. It's just showing you different binary performance metrics. The main one I want you to look at is the critical success index all the way down here. Okay, there's 2 columns. This is the performance on mask reconstruction on the synthetic images, and holo is the performance on just saying whether or not there was a particle in focus in the manually labeled examples in the first split. Okay, so I think it's pretty clear that the model trained with noise got a CSI of 86%, and the other one without noise was 16%. Okay, that's the only thing that's different between these 2 models. Everything else is the same, right? Same number of waves, same number of planes reconstructed. Everything else is the same. Okay, it's just that one's trained with noise, the other one was not. Huge performance improvement. That's on the holodeck images. But note that we sacrificed a little performance on actually reconstructing those masks in the synthetic images. We lost about 3 points as a result of gaining like 50 points on the other data set. Okay, so I'm happy to make that compromise. But we will see, and I'm going to show you here when I show a histogram, that where we actually lost that performance is on the very smallest particles. And that kind of makes sense, right? If you start like kind of throwing some noise into your images, the smallest ones you might lose them. Okay, and I think that's actually what happened. Okay, now if you stare at this long enough, and you can't hit pause on YouTube if you're watching this, you might be tempted to say that the model where I use 48,000 reconstruction planes, and remember, this is the one that gives me the same resolution in Z as in X and Y, you're tempted to say, well, that one had the best, right? I got 87.8 versus 86, and the same. It's not true. Okay, so I don't want you to get ahead of it. That's not the best model, and I'll show you why. Okay, now, so I'm going to come back now. That was just the training results, and now I want to show you the real results in 3 dimensions. So this is the operational pipeline where we search the whole hologram, and then we perform our 2-step clustering. Okay, so first, just focus on the top row here. All right, and what this is showing you on the y-axis is the number of particles, and the threshold that I used in the distance-based clustering is on the x-axis. Okay, if you look at the legend, there's a couple of different things in the legend. So the red dashed line is just showing you that there's always 500 particles in these holograms, right? By choice, we simulated them that way. Okay, the blue red dot, or the blue circle, is going to show you the number of clusters at that threshold. And then the orange squares will just show you the number of particles that have not been put into a cluster yet. Okay, the total is just the sum of those 2 things, because that's how many particles we're going to predict at the end of the day. It's the number of clusters plus the number of unassigned. Okay, so observe then that as I start from the left at a very small threshold of about 100 micrometers over here, and I start to increase this, and keep in mind, this is n equals 1,000 on the left, 1,000 on the right, noise-free on the left, noisy on the right. Right around that 144 micrometer, which is if you use 1,000 reconstruction planes, that's your delta Z, okay? So right around 144 micrometers, boom, loads of particles suddenly start jumping into clusters, okay? And then as we slowly, continually to increase this distance threshold, and remember, that's if the distance between 2 particles falls below that threshold, they're considered to be part of a cluster. Right, so as you increase that distance, more and more particles join clusters. Okay, then right around, somewhere around 1,000 micrometer threshold, we're predicting a total number right close to the true number. Okay, now if we continually raise this threshold, are like very large, right? If you have a threshold that's now 10,000 micrometers, you're pretty much putting most of the particles into one cluster. So that's obviously bad, but I mean, it's here for illustrative purposes. Okay, and this plot really does kind of show you like how sensitive our results are to this clustering threshold. Okay, so the middle plot, the plots in the middle, basically, which says the match fraction. Okay, so over here on the left, I'm kind of showing you like a match F1 and a match accuracy. You can kind of interpret these as to the left when the orange is above the blue, we're over predicting the true number. We have too many particles predicted, and you know I can't match 600 predicted particles against 500 true. So I have an excess of 100 particles. Okay. Likewise, if your distance threshold is way too large, right, then you're just massively under predicting the true number of particles. So I might only predict like 50 over here, and there's 500 true. Okay. And that's why you see these 2 curves, the relationship kind of flipping. So right here is when we're pretty much right at 500. Okay. Now the bottom plot is basically just showing you of the matches, right? If I predicted 450 total particles at some threshold, well, that means I can match 450 up against the 500 true particles in there. So this is just showing you the computed RMSE as a function of threshold. Note that when I train without noise, it's actually higher than when I train with noise, even though when I train with noise, I had a lower fraction. Okay, so I'll explain that shortly, why we see that. But you might ask yourself, there's only 500 particles in the true holograms. And yet, when I start out all the way over here on the left, before I do any clustering, it looks like I have more than 1,000 particles predicted. So why are we over predicting particles? Why do I even have to do this clustering in the first place? The reason is this false prediction along Z. Okay, so what I'm showing you here in the 3 rows is basically the same particle over here on the left, right? But it's one Z plane away. So note that this is some 45,464 away from the detector arms. And this was one delta Z before it. This is one delta Z after it. And that delta Z is 144 micrometers. So this is just zoom in. The second column here is just zoomed in of what you see on the left. And I mean, I can't really tell the difference between these 3. If you look at this bottom one down here, you can kind of start to see these rings popping in that I was talking about. I'm comparing, here's what the standard method said: no particle predicted, particles in focus in the middle, and then out of focus. Neural net said it was in focus across all 3 planes. Okay, so that's what's going on here. We're over predicting the same particle along Z. And this is why we actually had to use the clustering in the first place, because this is the same particle and I want them all in the same cluster. Okay. Part of the reason why this is happening is because of the way that I chose to upsample out of focus particles to in focus particles when I was training this neural net to begin with. And if you recall that of the negative examples, the tiles that didn't have a particle in focus, I basically said, give me a quarter that were one wave, one Z plane away, like these examples, and then the other quarter not. But that was probably not an ideal choice. So it's a naive choice to upsample 1-to-1. It is giving us performance, but there's improvement to be had there, okay? So the idea was that, okay, great. If I start off at some n, say n equals 100, and I keep ramping up the value of n, that should in theory give me more resolution along the z-axis, right, in predicting these particles. That was what we had hoped for. But as a result of the false prediction problem, we're not seeing that, okay? In fact, they're all about the same, 1,000, 5,000, 10,000, 48648. Maybe the 10,000 squeaked out a little bit here, but some of this is just due to the random weight initialization of the models as well. Now, I will say, I don't want to throw, I have a tendency to be very hard on our results, and I want you to note that the RMSEs in the 1,000, 5,000, 10,000, 48648, they're all pretty low. In fact, they're all under 100 micrometers, okay? In fact, they're all down around 60 or below. And I want to point out that the depth of field of the holodeck instrument is about 59 micrometers in and of itself. And that's right about what we're seeing here, right around this 1,000 threshold. You know, this is the threshold that we use to do the clustering, okay? So it's not even really clear based on the instrument itself that we could do better than that. But that was the objective here of trying to ramp up the value of n. Now, as a result, we're just gonna stick with 1,000, right? Because this one's gonna be 5 times slower, or I'm gonna need 5 times as many GPUs if I want it to be as fast as the 1,000. Okay, so obviously at this point, increasing n is really just making it fast. I need more resources. It's going to take longer to process. We're going to just stick with 1,000. And that's also what the standard method did. Okay, so at that threshold, I'm just going to pick 1,000 micrometers as our distance threshold. And this is just an average across the 10 test synthetic holograms. The top is the one trained without noise. The bottom is the one trained with noise. And remember, the one on the bottom is the one that's performant on the real holograms. The one on the top is not performant, okay? That one had a match. Oh, I just got ahead of myself here, apologize. I just want you to note that we had a higher RMSE when we had a higher match accuracy. Okay, we had a lower RMSE when we had a lower match accuracy. Okay, and I told you earlier that we actually lost when we introduced noise in the model. It made it harder at predicting the smallest diameter particles. And you can kind of see that roughly if you compare these two bins here, right? Look at how much, we missed a lot more of them over here, okay? So because the top one was able to predict a lot more of the smaller particles, well, then those were wound up involved in the clustering, okay? And it just so happens that the harder ones are actually more difficult to cluster. A lot of the times they wind up getting put into a cluster that they don't belong to, okay? And that actually winds up throwing off your RMSE. So even though we had a higher match accuracy, we had less accuracy in actually predicting the relative distances of our predicted particles from the true particles. Okay, but overall the model's good. I mean, 85% is still pretty good compared to what I'm going to show you now. All right, so this table here is now showing a performance comparison between our neural network and the standard method performance on 10 holograms, 10 holodeck holograms, okay? So basically I've just labeled them like 10 to 19, okay? This is just showing you how many examples were in these holograms that we manually labeled, that we manually evaluated every single one of these, okay? And true is how many particles we thought were actually in the holograms. I want you to note that holograms 16 through 19, we thought there were no particles in there, okay? Now I want to draw your attention again all the way over here to the CSI and just look at the red highlights. So this is the standard method performance, 67.6% on CSI, neural nets at 85%. Okay, so what is that, like 18-something% improvement with a neural net? Okay, and if you stare at these numbers long enough, you'll start to see a lot of things. Okay, and the one thing you'll notice is that when there's a fair density of particles in these holograms, the standard method and the neural net both do pretty well. Okay, the standard method has a higher false alarm ratio overall, but they're fairly comparable. It's these low density examples that seem to be really tripping up the standard method, whereas the neural net did not get tripped up by these. Okay, so note that we have pretty flat performance across all of these metrics for the neural net, okay, while it's almost always lower in the case of the standard method. Okay, so but the take home really is on this RFO7 split of the examples that we looked at, we're getting about a 20% improvement. Okay, so I want to show you just a couple examples of who got what wrong and where, kind of. Okay, so the top is the standard method, and note that we labeled it 0 and it predicted 1, right? So 1 meant, oh, there was a particle in focus. So here's another one of these wave reflections I pointed out earlier. Here's another one of these weird artifacts, right? And I said that we thought they weren't particles, okay? Now here's one that we labeled 1, and I don't know why it missed it. It just missed it, right? It's a small particle here. And similarly, here's another example where we thought that was a true particle, but it was missed by the standard method. If you kind of stare at these, they're not super circular, you know, they're kind of blurry around the edges. So they may not be particles. We labeled them to be true, okay? Now the bottom is showing you neural net examples. Now these are ones that we got wrong, right? It was labeled 0, but the model predicted 1, so some false positives, okay? And I mean, again, they're kind of, this one kind of doesn't really look that circular, right? It kind of looks like a half moon or something, or like, I don't really know what's going on over here. So we labeled this one 0, but I will note that these were actually labeled with relatively low confidence because we really weren't sure, okay? Now, examples that we had a little bit higher confidence on, but still not perfect. So this is one that we labeled 1 and the model predicted 0 in both cases, okay? This one kind of doesn't quite look so dark, right? It's got that little circle in the middle that I was talking about before, but we didn't have any other examples that were nearby this particle when we looked at all of them. So we said, well, I don't want to like miss this one. So label it 1, okay, even though the model was predicted 0, but we thought it was real, okay? Same thing with this one over here. It's probably just a small particle. I don't know why the neural net didn't get it. It's not perfect, but overall, the standard method mainly was getting tripped up on those examples that had very, very low density of actual particles in the holograms, okay? And this last histogram here really kind of just shows you potentially where things are going wrong, okay? And I want to note that the neural net has pretty much flat performance across X, Y, and even Z, right? It does about as well when the particle is close to the detector as to when it's farther away, okay? Now, if you look carefully at the standard method, it almost kind of looks like there's a little bit of a bias towards one side in X and Y, right? So notice how the error is a hair larger here compared to this side of the hologram, okay? I'm not totally sure what's going on there yet, but overall, both the methods do pretty well. It's just the neural net seemed to excel in some sense because it was able to pick out more particles, okay? And when it was able to do that, it made that mask prediction, and those mask predictions were pretty good all around, okay? So I just want to, I'm pretty much at the end of my talk, and I kind of want to just show one more slide with you. And this is basically showing a way around having to manually label. Okay, so obviously I noted that was very time consuming. We did more than 2,000 examples. That took like a couple of weeks to get 4 of us to actually go through all of them. They were lots of them were arbitrary. We had confidence scores. So it'd be great to not have to do that. But we still need to make our perfect examples shown on the left look a lot like holodeck examples shown in the middle. Okay, so one way you can do this is by taking advantage of something called a generative adversarial network, or in other words, a GAN, sometimes called a deep fake. I think there's been a lot of fear in the media as to deep fakes. What we're going to try to do is we have something in operation already, preliminary result, but the image on the right is actually a synthetic image that we passed through a GAN, and the GAN made it look more real. Okay, but the critical difference between the middle image and the image on the right is that we know where the particles are on the right. So we can use the images on the right as training data. Okay, so that was the whole point, right? Take out the manual labeling so that we didn't have to throw arbitrary noise in and then kind of just guess the noise parameters. Here, we're just saying no manual labels, except for the fact that we've labeled one data set holodeck and the other one synthetic. And I think that's a pretty fair label, okay? So just a little bit of where we're going. I won't get into too many more details on that, but if you're interested, do follow up, shoot me an email or something. I have to do a little PR for our paper. So it's neural network processing holographic images. If you just search for it, you can find it on the archive already. Here's the references that I promised. I'm going to come back to this. I just want to say my thank you to everyone, and I'll leave it on the references slide. So again, just want to thank everyone on the team, especially Matt and Aaron. Gabrielle as well. Gabrielle produced a lot of the figures that you saw today. This is the tech that we use. We kind of use a little bit of everything to get this to work because it was not the easiest pipeline to build, but we're pretty happy with the results. I'm going to leave it here on the references slide for you. So I'll take any questions if there have been any.
Great. Great. Thank you, John, for your dynamic presentation using machine learning to identify the holodeck cloud particles. I and others certainly appreciate your energy and enthusiasm in this research. Now I want to know more, even though it's not my, my area of expertise. We do have a few questions that are coming in. Again, may I please remind the audience to use the Slido interface below this presentation screen to ask your question. We have one quick comment from Jianmin Yuan saying nice talk. Thank you for that.
Thanks, Dr. Yuan. That's my PhD advisor.
Very good. Maybe there'll be a follow-up question. We have a question from Raymond Shaw who asks, so to be sure I understand, the GAN is a method of introducing realistic noise to the synthetic holograms.
That is correct. Yes, that's what we're going for, right? I mean, ultimately what the GAN, and if you think about it, I haven't actually like written the code this way, but what we ultimately really want to do is have the GAN learn the noise model, learn a noise model of the instrument. Right, because ideally you'd get synthetic holograms if everything was perfect, I guess. Or you'd get images from Holodeck that looked like the synthetic holograms. I think so. You know, absent noise. So that's kind of what we're going for. Yeah. Mm-hmm.
Okay. Excellent. Thank you for that question. We have a question from Clea Mahoney who asks, how do you make those cool graphics?
So most of the plots that I showed, those were actually just made with matplotlib, which is, I think other people are probably pretty familiar with that. I only showed one example of of us predicting particles in 3D. We're using Plotly for that. And Gabrielle has actually written a nice notebook where you can take our 3D, our particles predicted in 3D, and you can kind of rotate that around. Let me just. I can just show you really quickly here if I'm not sharing my screen, but yeah, that was made in Plotly, actually us visualizing these things in 3D.
I think, John, I think I saw in your summary slide that you have your stuff up on GitHub, a GitHub repo. So yep. People, is it if it's in a public domain then, or people who work at NCAR, then there's access to your notebooks?
Yep. Yes, okay. They're all there.
Excellent.
And all of the data as well can be found on Zenodo. If you just go into our archive paper, it should all be in there. The links to the code and everything is there.
Great question. Thanks, Clea. We have, it should be, for some reason, it's, I'm gonna try to highlight this question. Seems to be, there it's coming up. We have a question from Nithin who says, nice talk. How are the thresholds for the masks determined?
That's a good question. Okay, so actually the output of the model is basically a binary classifier, but it's a binary classifier on an image. So every pixel, right, is going to get a predicted probability. Okay. Now, ordinarily, in a binary class, if you're doing a binary classifier, the sort of naive thing to do is just say, well, if the predicted probability was less than a half, you label it 0. If it's greater than a half, you label it 1. I actually will do a threshold on that. So what we will try to do basically is find the best probability, okay, that maxes out some metric. Okay. So I didn't get into that in too much detail, but there is a calculation that I perform in order to determine what that probability threshold should be. And it's actually pretty high because the models are pretty confident. It's either yes or no for the model. So I actually think the threshold was like 0.9 or something like that. So if it was greater than 0.9, it would be labeled 1, else it would be labeled 0, right? So that would be the mask. That would be the mask threshold.
Excellent question. Thank you for that. My takeaway from your talk is that machine learning is really great for finding patterns and order, sort of much like self-organizing maps that use clustering techniques. The small diameter particles or your low density seem to be your nemesis. What more can be done, or what are your plans to get to that stage where you've trained it enough that your neural network predictions for this instrument are optimized for most image cases?
Yeah, and part of like our follow-up work that we're going to start doing is looking at more than just the subset of data, right? Where the real holograms were mostly like the best ones we could kind of find in some sense, because they were relatively clean. You didn't see too much interference patterns in them, and they had a lot of liquid particles in them. I didn't show you any examples of ice and like other weird artifacts that are in these that we have to learn how to deal with ultimately. But for the most part, the neural net didn't struggle with low density per se, right? It did okay when it was, the neural net basically didn't predict when it wasn't supposed to on the holodeck images, but it did struggle on those smaller ones. And that's not so easy to do, because a lot of these smaller particles are like a handful of pixels in this very large image. And we might have to look into that. I mean, we might be limited to a certain extent. And I noted it's about 3 microns in X and Y. And that's about what we're getting. So
Right.
I don't think we're kind of at the limit of diminishing returns, really, I think.
Do you think that you could use you would end up having to use a combination of both a neural network and a standard method, and the standard method combined, like where you pick and choose where one predicts better than the other?
Yeah, I almost kind of have that in mind, because a lot of our pipeline was us failing at other things that never wound up working, and then looking at the standard method and being like, well, why does that thing work? And the wave prop was sort of the key thing that we borrowed from what the standard method does. And that was, in a lot of ways, that's kind of what reduced the machine learning problem to, oh, I just have to pick out a dark circle in an image. Like, that's not that hard, right? I worked in e-commerce. I had to like decode language into e-commerce speak. That's a way harder problem. So in a lot of ways, it was kind of really trying to simplify what the neural net was supposed to do, I think.
Yeah. Thanks. That was a great. We have one final question from Raymond Shaw, and he asks, when all the steps are put together, reconstruction at n depth, CNN, stitching together in both dimensions, etc., how does the performance compare to the standard methods? I mean, in terms of computation time. Very cool work. Congratulations to all of you.
It's still fairly computationally intensive. I mean, I need a GPU, and now I have some benchmarks in the paper where I used a single GPU and a single core to evaluate the neural net. And Aaron Bansheimer was the one who was doing the standard method, and we put some notes in there as well. They're pretty close at this point, really. And the neural net, I mean, the neural net is faster because of the massive parallelization that we built into it. And in some sense, like a lot of that could be replicated with the standard method too. Like you could process, n planes simultaneously as well. But I mean, I will say that we had to do the wave prop was not what we wanted to do. We wanted to take the image, the full size image, maybe tile it like I explained, but not do the wave prop. What we really wanted to do was just be like, fine, there's 500 particles in the image, pass it through, give me 500 particles back. We could not get that to work. And I think it was just because the Z range is so large that a lot of particles just are totally out of focus. And there's quite a good number of neural net applications in the literature right now. And you will note, if you've been reading them, that they do a much smaller Z range than we do. So I don't know that if we want to really speed this up, we probably should try to reduce N. And in fact, N equals 100 reconstruction planes, like actually gave a pretty good result. And that's 10 times faster already. But at the end of the day, I mean, it was really the parallelization is what we're leveraging for sure. Yeah, the neural net was kind of like a detector, right? Particle, not particle. And then if there was a particle, it was, okay, try to draw a circle, a filled in circle around it. And thanks, by the way. Yeah.
Great question, and great way to end the seminar, because we are past the seminar hour. If you are interested in Dr. John Schreck's presentation and have further questions or want to collaborate, please reach out to him via his email, which is provided on the seminar flyer. On behalf of EOL and CISL, I would like to thank Dr. Schreck on his illuminating presentation using neural networks to improve holographic images using our Holodeck cloud probe. And may I remind everyone who's listening that we have another seminar next Tuesday given by Dr. Matt Heyman, the colleague of Dr. John Schreck, who will talk about EOL's micropulse dial instrument. Thank you, everyone, and have a great day.